okay, we would expect to make the most out of the well with the equivalence point, right? We've used up all the reactant. So, if we use up 2 drops of lead stuff and 4 drops of potassium stuff, is there a place where we actually use up more than 2 drops of this or more than 4 drops of that? No. So, we would expect that second well to have made the most product. What happened? Because it settled out enough. So when you look through the side of these well plates, you should be able to see a little pile of yellow stuff. My old eyes aren't having a lot of luck with that. And it might take a little while for it to really settle thoroughly. So we can wait a little bit. You don't want to jiggle it around and try to kick it back up. But we'll pass it around and see if that second well, that would be this one here, second from the end, if that is the one that made the most precipitate. Does our actual occurrence agree with our math? And it should, but you never know. But you can see how it's settling. You can see a solid that has settled there. Mm-hmm. But it's not completely settled out yet. There's still some yellow stuff kind of floating around that hasn't completely settled. And those little well plates are even harder to see. So we'll pass that around in a little bit and decide if we really see it. You don't have to write a lab report on this. I just want you to get a little experience with mixing reactants. And to really understand, like when we look at the ratio of reactant to reactant, and we compare that to the ratio in the balanced equation, how we decide where we would expect the most product or the best outcome to be. So to continue on with this experiment, if we had everything we need, we could do this on a grander scale. And what we're going to do is kind of pretend we're doing it without actually spending the money on the chemicals with this sheet. So if you go ahead and grab this sheet, we'll come back to this once this settles well and see if we can see what we made and how much is in each well. But it does take some time to settle out. So, we'll need a calculator. Oh, is there an extra laying around? Thank you. Did you get the other one? Yes. Okay, good. Does that have a back? Yep, okay, good. Alright, so you're investigating the precipitation reaction occurring between aqueous lead nitrate and aqueous potassium iodide, which is exactly what we did here. 2 colorless things produce a colorless liquid and that big yellow solid. So it says balance the following equation, which is on the board, so that should go well. But do make sure you have it balanced correctly on your paper, or there'll be trouble with the rest of the math. Oh, it looks like Module 16 appears on my paper for some reason. I guess we'll come back to this again later. Alright, so when your equation's balanced, here's what you would do in the lab. Then you weighed out 1.02 grams of lead nitrate, right? You take a scale, you weigh it out, and 3.11 grams of potassium iodide, and you dissolve them each in a flask of water. Okay, so that's exactly how I would make these 2 solutions. Right? Like the lead nitrate is starting to run out. The potassium iodide I actually made more of last year, so I have a big bunch. But the lead nitrate is running out, so I'm going to have to actually do this to make a new solution. And it has to be the right concentration and everything. So I have to, and you'll learn in Module 10 how to do that. But I'll weigh out the powder of the lead nitrate, I'll dissolve it in water, and I'll pour it in a little dropper bottle. That's how you make a solution. Maybe we'll make a new one for me in Module 10, because I definitely need some. And so you make these 2 solutions. You dissolve 1.02 grams of lead nitrate in some water and 3.11 grams of potassium iodide in some water. When they're mixed, so you take some of the lead nitrate and some of the potassium iodide, you mix them together, and you observe that a yellow precipitate is formed. You guys have seen this happen. So that yellow precipitate is the lead iodide, a water-insoluble yellow solid. the other product, potassium nitrate, is water soluble. It would be a white solid if it weren't dissolved in water, but since it is dissolved in water, it forms a colorless solution, so it's aqueous. So what if I wanted this lead nitrate, or this lead iodide, I mean, what if I wanted that yellow stuff? What if Mr. Shelton needed some yellow paint, and I wanted this yellow stuff to make paint out of? What would I do? How would I get it?
You filter it out.
Okay, so take some filter paper, filter it out, and then how would I make sure that it wasn't contaminated or?
You could do the thing that we did where you spray it with the water.
Right, I should have rinsed it better. Yeah, definitely. So filter it out, rinse it, and then dry the water out of it. And I'd have the lead iodide reclaimed. So you filter the solution through filter paper. Before you do that, you weigh the piece of filter paper so you know how much it weighs, because it's really hard to scrape your whole sample off the filter paper accurately. So here's a key point when you're doing labs in college: weigh your glassware, mark how much it weighs, weigh your filter paper, mark how much it weighs. You might need to know that at some point. So you want to be able to subtract out the weight of things that don't actually matter, that aren't the chemical you're experimenting with. So you weigh a piece of filter paper and you find a mass of 1.89 grams. Why do we choose filtration to separate this mixture of lead iodide and aqueous potassium nitrate? Really?
Tweezers won't work.
Yeah, tweezers would be really, really challenging in this situation. So whenever we're separating by physical means, we compare the physical properties of the two things. Anything that's aqueous is going to pass through filter paper. Dissolved salts have tiny, tiny particles that go right through. And solid things that are insoluble in water, they don't go through filter paper. So just basically, we chose the physical properties of size of particles, and then we were able to separate them. We could have, compared other things: boiling point, melting point. We could have compared, just magnetism. Neither is magnetic, but if one were, we could have separated it that way. And you just look at physical properties, pick the easiest way to separate based on their differences, and do it. Filtration is easy, cheap. So what if then I filter it through, wash it through? What if I needed that potassium nitrate for something? How could I get it back? It's dissolved in water. Evaporation. Boil off the water. All these salts have very high melting points and extraordinarily high, boiling points. Water, of course, is low, so it's easy to reclaim the salt out of water if you need it. I don't want the potassium nitrate there with the lead iodide, so that's what we're going to do. We filter it out. We dry that filter paper, put it in an oven, try to get rid of all the water. The mass of the dried filter paper and the lead iodide was 3.34 grams. So now we need to know what is the mass of the lead iodide without the filter paper. Good thing we weighed the filter paper in the beginning, right? So go ahead and calculate that. All right, what do we get? How did you find it?
1.45 grams.
Good. So we had 3.34 grams for both the filter paper and the lead iodide. We subtract the mass of the filter paper, which 1.89 grams is kind of a massive piece of filter paper. I don't know what I was thinking there. But there you have it. So you find that just the lead iodide without the filter paper has a mass of 1.45 grams. So now use your periodic table to find the molar mass of lead iodide. And then also you're going to need, lead nitrate. You're also going to need the molar mass in 6 of lead iodide. So do both of those real quick. You can talk to your neighbors. And then 7, you need the molar mass of Ki while you're at it. So you can.
I don't have one.
Oh, you don't have a periodic table?
Um.
I'm going to hit pause.